So we will start with the 5 postulates we introduced last time, and we did this in our homework. Because this is very important, a little bit abstract. We will do it several times. Okay, I start with Aaron. What's the first one?
A straight line can be drawn from any point to any other point.
Okay, give 1 point, another point. We can always draw a line. Okay. Moreover, this essentially says there's unique line. There's exactly one. One and only one. Okay. Second one. Okay. Kira, what's the second one?
A straight segment can be extended infinitely in a straight line.
Okay, so if we have a segment, extend this to a line. Three. And Fred, P3, third postulate.
See, the P3 is a straight line, but only one side has, if only one side that lies through the point.
Okay, so the third one, it should be about circles. We can draw a circle for any given point and the radius. Okay. For any point and any number, we can draw a circle centered at this point with this radius. We call this the fourth one is that all right angles are the same, have the same measurements. Or we should see the congruent. Straight. And the fifth one, we also call it the parallel postulate. if these two angles, the measurement of the two added together is less than 180, then the two lines intersect. The implication of this is then the summation of the two angles must be in this case, we say they are parallel. This is why this postulate is also called parallel postulate. Okay. Now give a summary of this parallel, two lines being parallel. Angle criterion. Okay. We'll consider two lines and a transversal. Then the following are equivalent. Okay. So this is the summary of what we have proved from last time. The two lines are parallel. The summation of two interior angles on the same side and the third one, the corresponding angles. We have four pairs of corresponding angles. Each pair, they have the same measurement. Some will say congruent. It depends on how we view these angles. Do we view this as the measurement? In that case, we say equal. Or do we view them as the geometric object? In this case, it was congruent. Depends on our viewpoint. So I list both. Similarly, equal or congruent. It depends on the viewpoint. They are different. And it depends on the viewpoint. If we draw a picture of this, you will have a better understanding of what we are talking about. One, two, three, four. So the second one will be the summation of angle 1, angle 2 to 180. The corresponding angles, 1 and 3, the corresponding angles. Alternate angles, 1 and 4. Okay, here we view them as measurement. If you view them as geometric object, we should use congruent. Right. Okay, so we have proved this, and in the future, we will use this statement without proving it, because we have done the proof. Okay, any question about the 4? Okay, next we will introduce the triangles that you are very familiar with. Aaron, how do we define a triangle?
Define,
Maybe describe either way.
okay, three-sided shape.
Okay, so as when we have a geometric object with 3 vertices and 3 sides or 3 edges. Okay. I'm going to draw 3 lines. This time, let's mark them. Just A, B, C. So we have a triangle there. This 3 intersections because the 3 vertices. A, B, C. And the 3 sides or 3 edges. We have AB, AC, BC. Okay. Here, as we have done before, when we see an angle, it has 2 meanings. One is for the geometric object, one is for the measurement. We have the same situation when we see the sides. One, it means the geometric segment over there. But we also use this to represent the length of the segment, the size. Okay, so double meaning. Geometric object. The segment. So we can, in this case, AB will be this segment. If you draw a different one, even they have the same length, it will be different segments. Same many measurements. the length. Okay. In this sense, if we have two segments, sometimes we will see, let's say A, B, E, F, A, B congruent to E, F. Amy, yes.
Oh, I wasn't raising.
Okay. So if we treat both as geometric objects, we say they are congruent if we can move it to there, then overlap. Or we write AB equals EF. In this case, we say they have the same length. So be careful. So our notation, so there may be some ambiguity of our notation. There's some advantages and disadvantages. The advantages, it will be simplify our study. But you should be careful what the meaning for this object that we are dealing with. Are we dealing with the length or are we dealing with the geometric object? You should always be careful. Okay, some more geometric objects. The interior angles, we have three interior angles. We call this alpha, beta, gamma. We also have three exterior angles. For example, we start from a B. It's the supplementary angle to angle beta. This is one exterior angle. Supplementary angle to the interior angle, another exterior angle, another exterior angle. Okay, let's call them A, B, C. Okay, so again, you are very familiar with the interior angles, alpha, beta, gamma, at each vertex of the triangle. We also introduced the exterior angles, supplementary angle to this. Okay. Now we have two theorems about these angles. I think you all know the first one. Where's the theorem? The sum of the three interior angles Aaron, what's the sum?
Let's see. For the three interior angles,
Of a triangle.
okay, 180, I think.
Of any triangle.
At least 180, I bet.
is exactly 180. Amy, what do you say about this? The sum of three exterior angles are A, B, C.
Is it 360?
Okay, how you get that? Correct.
Because I think so the inside angles add up
Mhm.
to 180.
Mm-hmm.
So the outside would be like the 3 supplements
Mm-hmm.
of
Yes. Mm-hmm.
those
Mhm.
3.
Okay, nice. Okay, so we will go over that later. So first, the conclusion is, okay, so let's give a proof for each one of them, and then we show that these two are equivalent. I will draw an arbitrary triangle. Okay, so you can see when I say I draw triangle, I actually draw 3 intersecting lines, and you will see why I draw these lines instead of the triangles. To prove this, let's draw a parallel line through this point. We will draw a parallel line. Okay, use different color. Okay, we have, this will be A, B, C. This is alpha, beta, gamma. Now I want to prove the summation of the 3 is 180. One way to prove this is want the summation of these 3 angles is the same as the summation of these 3 angles. If we can prove this, then this is a flat angle, so the total will be 180. Kira, does this make sense? Is this logic to you? To prove,
Sort of, but then how would you prove that? Oh, wait.
okay.
I
Okay, so
should've-
first, I want you to check, are these 2 angles the same? Let me use different color. I will put put angle 1 here. I want you to check, Kira. Beta and 1,
So it's using the
are they the
like
same?
the alternate angles.
Yes.
So it's basically
Okay,
like
so
okay, I get it.
okay, so that's why we have this over there. If 2 lines are parallel, then the alternate angles are equal. So now we have an application. These 2 lines are parallel by construction. Then these 2 angles, they're alternate angles. Therefore, they are the same. Okay, so first step, since the two lines. Fred, now we consider another one, angle 3. Can you tell me if these two angles are the same? Gamma and angle 3, Fred, are they the same? And why?
Because first, 1 and beta is same.
The angle gamma and angle 3.
Yeah. 3. Angle 3. Then can you explain why the gamma equals 3 or
So we wanted to claim this gamma.
why? Like first, the angle 1 equal angle beta.
So angle 1 equal angle beta because these two lines are parallel and they form a pair of alternate angles. It's the same thing here. These two angles are the same because they are the alternate angles. Okay, now we can see that with these two preparations, the summation will be alpha. Beta is same as angle 1. Gamma is same as angle 3. Now we can see the 3, it gave us a flat angle. Therefore, this is 180. Okay, any questions? Sophie, can you hear us, Sophie? Leave a message. Okay, now we will prove the second one. The summation of 3 exterior angles. Okay, to do that, we will do the same thing. I will draw an arbitrary triangle. 3 lines, I don't care whether I want it to be different. I want to be different. Okay. Okay, the same thing, I will draw a parallel line. Which way? Let's go this way. Okay, it's about parallel. Okay. The proof of theorem 2. We finished the previous one. I'm not sure you have seen this before. QED. Have you seen this before in your textbooks? Aaron, have you? No, okay. Amy says no. Kira, what about you? No, okay. So this is short for question ended desired. So it's the finish of the proof. It's the same thing. Okay, let's label the 3 points. Label this as A, B, C. The 3 exterior angles. This is the interior. interior, interior, the exterior. This will be let me see, how do I let me move this a little bit. Is this okay? Okay, nice. So this will be our exterior angle A, exterior angle B, exterior angle C. Mhm. We want to check.
Why aren't we using alpha, beta, and gamma? for that?
Okay, alpha, beta, gamma for the interior angles. Alpha, beta, gamma. We have used already.
Oh,
Okay. Mm, Okay, first, this angle is also C because they are the vertical angles. Then I claim this angle. So get rid of this A. Angle 1. I claim angle 1 and angle C are the same. Same measurement. Aaron, can you tell me why they are the same?
oh, that one. Well, they are corresponding.
Okay, because they are the corresponding angles. These two lines are parallel, they are the corresponding angles. Next one, I'm going to remove this alpha, beta, and gamma since they're interior angles, not useful for this proof. Save us some space. Next, I wanted to check angle 2 and the B are the same. Let's see why. Amy, what do you see? Why these two angles are the same?
They're like alternate
Yes, they are alternate
interior.
angles for these two parallel lines. Okay, now we can see if we add the three exterior angles, A, B, and C together. This will be the same as A to 2 angle 3. Not sorry, 1, 1. So we have A, 1, 2, and this is goes around one loop, so the total will be 360. Okay, then we finish the proof. Aaron, what do you think of this proof?
I see there
correct?
I see there are two angle Cs. Which one?
Try that again. I'm sorry, I didn't follow. What's that?
I see there are two angle Cs.
What does that mean?
I see two of those angles marked with the
You
C.
labeled C twice,
Yeah.
Okay,
or
so
3 times actually.
okay, so here we should see these two angles have the same measurement, right?
Okay.
Why, Aaron?
Oh, because the lines parallel, I see.
No, so these two angles.
Oh. Oh, they're obtuse, I see.
Okay, because they are opposite angles. So they are the same. In the same way, this one and this one, they are opposite angles, so they have the same measurement.
Oh. So they all make 360 that way, I see.
Okay. So we want to add the three exterior angles. We can add these three, or we can add A, B, and these three, because these two angles, they have the same measurements. Okay, Kira.
For the like A1 and 2, does one go all the way to like the other parallel line, or is one just that?
Okay, so
And
how
2
do we
is also.
decide? We want to use this 1 and C, they are the same. This C from there, so these two lines, one transversal. So the angle is from the line, the transversal. So here it's also from this line to the transversal. So it's the whole angle. Okay, then so these two theorems, we give different, maybe similar proofs. But actually, as Amy pointed out before, these two theorems are equivalent.
你能不要动啊？不要动好吗？
Okay, Jessica, there's some noise over there. Okay. So the theorem 1, theorem 2. To check this is that, let's go back there. This is a pair of supplementary angles, a pair of supplementary angles, a pair of supplementary angles. Let's write that down. Okay, they're similar, that's intention because they are related. The supplementary angles. I intentionally choose alpha, beta, and AB. Three pairs of supplementary angles, if we add all of them. So this. Now if we prove that this is 360, this is 180, then one implies the other, because the total will be 540 degrees. then is the same as in this way we see the two theorems, they are equivalent. Okay, so the two theorems, one about the interior angles, one about the exterior angles. For all of you, who favors the interior one? And who favors the exterior one? Kira, which one do you like more better? Interior or exterior?
Not really any preference.
Okay. Aaron, what about you? This one, interior angles or exterior angles?
Well, I'd say interior or exterior, they're both fine.
Okay, very nice. We will have a break, and after the break, I will show you this exterior formula is more intrinsic. So it applies not only to triangles, to equilaterals, to general polygons. We all have the formula. But for interior angles, it's completely different. The changes when the shape changes. Okay, we have 5 minutes break.
What's
We'll
a
be
general
back at,
polygon?
okay, yes. In the end, we have the polygons.
So what's a general polygon?
Okay, let me draw one example. Okay, kind of arbitrary. I want to make it even more arbitrary. Okay,
What?
okay, so that's a polygon.
Okay.
It's a general. Okay, so P. So polygon. Poly means multiple shapes.
I mean, but what's a general? But what do you define a general?
Okay, so this is a special one. It can be an arbitrary one.
A what?
An arbitrary one. You can draw anything you like. You can draw let's see, 1, 2, 3, 4, 5, 6. This one has 6 edges. You can
Okay.
draw with 10 edges, maybe 100 edges. So this is the polygon.
Okay.
Mhm.
So that's a general polygon. Okay.
Okay. Some maybe actually just the polygon, not a general polygon. Okay, so 5 minutes break. Okay, the two theorems. First one, the sum of 3 interior angles of any triangle is 180 degrees. Second one, the sum of 3 exterior angles of any triangle is 360 degrees. Now we want to see this one is also true for quadrilaterals. Let's consider 4 lines. General lines, I don't care if they're parallel or not. Just want them to intersect. Okay, so now we have 4 points. We can label their interior angles. To save us some trouble, I will use 1, 2, 3, 4. 1, 2, 3, 4. And I will label the exterior angles. I will go with 5, 4, and rather 5. 6, 7, 8. The good thing about the exterior angles, no matter what shape we have, the summation of exterior angles. It's similar to what we have for the triangles. Triangle. One, 2, 3. So for this one, we can see if we keep track of our direction, initially we start from this direction. Okay, starting point. At this vertex, we make a turn this direction. Okay, this angle 1. Then at the next vertex, we have the same direction as we ended. Then we make another turn, the new direction. Then we make another turn. The important thing is after 3 turns, we return to the initial starting direction. So we make a whole turn over the. If we only keep track of the directions, we make a whole turn when we add the exterior angles. Whole turn. Then in the end, we get back to the starting direction. Start from there, ended from to there. We can do the same analysis for the quadrilateral. This will be our starting direction. It's starting. We make one turn at this vertex, we go to this direction. Another turn at this vertex, we go to this direction. Another turn at this vertex, we go to this direction. Fourth turn, we go back to the initial direction. In this way, we make a full turn of our directions. Therefore, the summation will be 360 degrees because we make a full turn. We start from there once, twice, 3 times, 4 times. We return to the initial one. Aaron, is this clear or maybe I can explain it again? Why the summation of the exterior angles is always 360?
You're making a 90-degree turn each time.
So yes, so the total one turn, another. So like we are driving a car. Maybe that's easier. Driving a car around this geometric shape. At each vertex, we make a turn. This vertex, we make a turn of the exterior angles. We make a turn of the exterior angles, make a turn of the exterior angles, then we get back to the starting position. So we make a full turn after we go through all the vertices.
I see.
A full turn.
Wait, so basically that's basically just a 90-degree turn, basically.
Uh-huh. So in a special case, if you have a rectangle, we make 4 regular turns. They are all right angle turns. Here in the general case, each turn may be small, may be large, but the overall is still a whole loop. You can see no matter whether we have a triangle or a quadrilateral, the summation of the exterior angle is the same. So sum exterior angle. Okay, now let's see what happens to the summation of interior angles. For the triangle, we know the summation will be 180. For triangles. Okay, what's the summation of the interior angles of this quadrilateral? Any guesses? A hint using Amy's argument. Okay, you may ask which argument. So Amy maybe has several arguments. Okay, who wants to try? Kira, what do you think?
You can, first of all, you can tell that the 4 interior angles are like supplementary to the 4
Okay,
exterior
yes.
angles.
Uh-huh.
But then
Yes. Yes. Uh-huh. Yes. So we have 4 pairs of supplementary angles. Pair here, pair here. Each pair will give us 180, another 180, another. So if we add all of them, we get 4 times 180. And the exterior is 2 times of it, so we have 2 left. It will be 2 times 180. Okay, now we can list it over there. It will be 360 times 4 quadrilaterals. Okay, now let me draw 5 lines. 1, 2, 3, 4, 5. Okay, we have 5 interior angles. Let's label this 1, 2, 3, 4, 5. 5 exterior angles. Let's label this 6, 7, 8, 9, 10. The summation of the exterior angles, we can let's start from here. We make one turn, a second turn, third turn, fourth turn, and fifth turn. After 5 turns, we return to the initial direction. Again, we make a full turn. So the summation of the exterior angles is again 360. Aaron, what's the summation of the interior angles?
180. I mean, no, 180 is only for triangles, so therefore, hold up, let me see that. Oh,
What method should we use?
oh yeah, right. Okay, so that would be well, okay, so that would be around I'm saying I'm giving an estimate because I can't directly calculate this, but I'll say 400.
Okay. So here we will apply the same thing. If we add them all together, one pair of supplementary angles, another pair, another pair, another pair, another pair,
That'd be 9 times.
total 5. Mhm.
That'll be 5 times there's 180.
So the total will be 5 times 180.
Right.
Then we subtract the exterior angle. So we end with
Okay. Oh. Right.
I do not simplify. So now we can see this will be five edges. I'm going to write 5 lines. Then I can rewrite the previous one. So this took as so 1 times 180. So this will be 3 minus 2. It will be 4 minus 2. So 5 minus 2. Now we have the general formula. The summation of exterior angles for angle. That means a polygon with n sides. The summation of exterior angle is always 360. and the summation of interior angles. Minus 2, 180. Now, no matter what, how complicated the n-gun is, number 100 size, 1000 size, the summation of the exterior angles is always the same. We have a triangle, a quadrilateral, or 5 guns. The exterior angle is always the same. And because summation of this, we have n pairs of supplementary angles. Oh. So because the summation of exterior plus interior equals n. Okay. Therefore, we have the formula for interior angles. Yes, Kira.
For the sum of the interior angles for the pentagon, it's 5 times 180 minus 2 times 180. Where did the 2 times 180 come from?
Okay, so here, if we add all of them, we get 5 pairs, right?
But then you subtract the ones from the outside.
Yes.
Okay.
Then we subtract the one from the interior. So the total subtract the exterior, that's the interior. Same thing here. The total subtract the exterior, left with the interior. Okay, very nice, very nice. So now we can see is for some mathematicians, they prefer the exterior angle because this formula is kind of intrinsic. Okay, next, we will consider the congruence of 2 triangles. Okay, to save us from writing down this word every time, I'm going to use this symbol for a triangle. Triangle A, B, C, and triangle E, F, G. Okay, we'll use the notation. Triangle A, B, C. Congruent triangle E, F, G. If that means they have the same length. They have the same length and draw to B, C, F, G. Okay, so two triangles, A, B, C, and E, F, G, which they are congruent if the edges, this pair same length, this pair same length, and this pair same length. The corresponding angles A and E same measurement, B and F same measurement, C and G same measurement. When we write down this, we have to match the angles, the vertices, match the edges. In particular, if I switch two vertices, if I switch the two, then the triangles maybe not congruent. Okay, so these are different congruences. So this one, A with E, B with F, C with G, the order matters. If we change the order, it's a completely different relationship. Completely different.
Doesn't it have something to do with the side angle side theorem?
We will come to it.
Okay.
Okay. Okay, we will come to that. We have this side angle side, side side side, angle side angle. Okay, so how could we prove that they are congruent? If we can superimpose, if we can put this on top of that, such that the vertices and the edges, they overlap, then they are congruent. So superimposition. One put one on top of the other. Okay. Then we'll have several tests. So this definition have 6 requirements. Sometimes we want to reduce. I want to say that what's the minimal requirement? The first one is a test for congruence triangles. We will use this SAS for short. To pick the first letters. So given 2 triangles, suppose if we compare with the definition has 6 requirements. Now we have 3 of them. If we draw okay, it's fast. Works. E, E, C. We have A, B, E, F, B, C, F, G. Angle B, angle F. So this theorem is that if we have this 3 requirements, then it's enough to conclude the 2 triangles are congruent. So how do we prove this? To prove this, we will use this superimposition. If we put this on top of A and B, with F on top of B, because they have the same length, E will be on top of A, because they have same length. Because the 2 angles are the same. So this line, will be on top of that line. And because they have the same length, so G will be on top of C. So if we superimpose this, so this will be our F, because it has the same length, so E will be on top of A. Because the angles are the same and the same length, so G will be on top of C. Now, so this AC and EG, they also have the same length. The angle A and E, because they overlap, they have the same measurement, so we have the condition we need. Okay, so the proof. very important theorem. Okay, we will have a simple application. A simple application will consider a special family of triangles. So this is called the okay, where is it? Isosceles triangle. Mhm. Geometry is very simple.
Wait, isn't there two other types of triangles?
What's that?
Aren't there two other types of triangles?
Are there two types?
Two other types.
Yeah, what are they?
I think I forgot, but I think one of those right triangle and the other ones. I forgot what the other one is.
Okay.
There's
Yeah, so
there's right triangle and scalene, which are
Right, scaling, yeah, that one.
okay, so we will have more triangles in the future. Okay, so this one because it's a very nice application of our side angle side theorem. We want to have a interesting application. A, B, C. Isosceles means the drawing is not that. Let me redraw this. Same size, same measurement. Okay. So here again, we consider the length, not the geometric object. We consider the measurement, not the geometric angle.